Our next speaker is Dr. Rashid Abdullah, and he's going to be talking on unravelling the complex basement geology via SADM, an example from the Mount Woods domain of the Gawler Craton. Rashid is a senior geologist working with the GSSA since December 2022. Currently, he's involved in the compilation and attribution of the spatial data from the South Australian Discovery Mapping Project. Rashid did his PhD degree from the University of Queensland, where he worked on the Thomson origin of Eastern Australia. So I'd like you to welcome Dr. Rashid Abdullah.
Yes, thanks, Peter, and thank you all. I'll show how our South Australian Discovery Mapping Project helped us to unravel basement complexities of the Mount Woods from the Gawler Craton. So the Gawler Craton in South Australia has a complex geological history of sedimentation, polyphase deformation, metamorphism, and magmatism since the Mesoarchean. This complexity is particularly obvious in the north, in the Mount Woods area, where it preserves the Paleo to Mesoproterozoic tectonic processes. The Mount Woods domain is located to the north of Christie and Olympic domain. More specifically, the area occupies a key position to the north of the Olympic copper-gold province. Existing mine in the area includes the Prominent Hill, the Peculiar Knob, and the Cairn Hill. Despite numerous recent studies, there is still uncertainty about the tectonic evolution of the area. Solving this knowledge gap may help in understanding the tectonic processes and deformation history of the entire craton. So my research questions are, what are the kinematics and 3D geometry of the major structures or shear zones of the Mount Woods, that is the style of deformation, and how did these structures or shear zones evolve in time and space, that is the timing of activation or reactivation history of these shear zones and the relationship to the regional stress regime during tectonic events. And finally, how does this structural mapping of the Mount Woods can help in understanding the tectonic evolution of the northern Gawler Craton. So to address this research question, we aimed at generating a high-resolution systematic 1:25,000 scale geological map of poorly exposed Mount Woods domain through South Australian Discovery Mapping Project. Outcropping basement geology rocks are rare in the Mount Woods. As you see, there are only few bits. So we mainly rely on the geophysical data, existing boreholes, geochronology, published maps, and literature. Using this map, we established the overpainting geological processes to constrain timing and kinematic histories of the major shear zones, which allow us to relate these structures to specific tectonic events in different time slices. The oldest stratigraphic unit in the Mount Woods area includes the early Paleoproterozoic Mount Woods complex. It has two subdivisions. The metasedimentary part is known as the skylark metasediments, which includes mainly metapelagic to calcilicate rocks, and the age of the skylark sediments is like 1750 million years or older. These metasediment rocks are metamorphosed to amphibole to granulate facies. The igneous component of Mount Woods domain is Mount Woods unit complex 1 and 2. These are mainly orthogneises, and these rocks don't have any age constraint. Late Paleoproterozoic units in the Mount Woods includes Condamina metaconglomerate and engineered adamantiolite. Engineered adamantiolite is intrusive rocks that is like 1690 million years old with an error bar of 25 million years. And this can be correlated with the Tangila suites of the southern Gawler Craton. The metaconglomerate part is representing an unconformity, and it has almost similar age of the engineered adamantiolite. The Tandule time slice, we have the Balta granite or the Hilltaba equivalent granite and the Gawler Range volcanics. Gawler Range volcanics mainly occur to the south of the southern overthrust, and the age of the Gawler Range volcanics is like 1590 to 1580 million years. The Balta granite is slightly younger, ranging from 1590 to 1560, and mainly it occurs all over the Mount Woods area. And the youngest time slice in the area is the Mesoproterozoic, and it includes the Pandora Formation in the south and unnamed granite mainly in the north. Three major tectonic events in the area are the oldest is the late Paleoproterozoic Kimban events, ranging from 1735 to 1690 million years. And this Kimban event is mainly from the central part of Mount Woods. And subsequent deformation includes the Paleo-Mesoproterozoic Carran events. And these Carran events resulted in intense deformation and metamorphism throughout the Mount Woods. And the age range of Carran events is like 1580 to 1540 million years. The youngest event is known as the Korabi event, and that's age range is mainly 1470 to 1450 million years. The Karran and the Kimman events are mainly based on metamorphic ages of zircon and monazite, but the Korabi event mainly based on the biotite ages. So our interpretation starts with the interpretation of the Boger gravity data. This Boger gravity map shows that the Mount Root is mainly broadly a gravity high. This gravity map is also used to map the major shear zones, which are also the boundaries of the domains or subdomains within the Mount Roots. So for example, we have this Bulgania shear zones, which is running almost northeast, and this is the boundary between Mount Roots and the Cariolo Basin in the southeast part. This east-west turning southern overthrust, which has become almost like northwest turning, is the boundary between the Christie domain and the southern Mount Roots. The Skylark Spire Hill shear zone is the boundary between the central and southern Mount Roots. Both this southern overthrust and Skylark Spire Hill shear zone, they terminate against this Bulgania shear zone. So this indicates that possibly these structures are relatively older compared to Bulgania. In the north, we have this Cairn shear zone, east-west turning. This marks the central and northern Mount Roots boundary. To the further north, we see this northeast turning Curry shear zone, which marks the boundary between Coober and the northern Mount Roots. This Curry shear zone becomes more east-west, and where it becomes the boundary again with the Christie and Coober. So our main interpretation starts with actually interpretation of the aeromagnetic data. This interpretation shows that the Mount Roots area has very complex structures, and this structural complexity, kinematics, and timing of the structures are not uniform throughout the Mount Roots. We can see in the central part we have more ductile deformation or ductile to brittle deformation, which is evidenced by these refolded structures in the center, even here. But in the south, we see more brittle deformation, as well as in the north, we see more brittle deformation. In the south, we had this southern overthrust that has like more thrust duplicates, and this Skylark Spire Hill shear zone is more like a dextral, it has a lot of dextral offset. And both the faults, they are sinistrally dragged by this Bulgania shear zone. In the further north, we see this Cairn shear zone terminate the older structures, older fabrics of the central Mount Roots. And if we go, the same so it indicates that possibly this, in this part, this reverse fault. But if we go further west, we have some dextral dragging of this Balta granite by this Cairn shear zone. If we go even further north, we see this Curry shear zone. It has like sinister dragging along these faults, and also some reverse reactivation, younger reverse reactivation. But if we see in the eastern part of the Curry shear zone, it becomes like the early phase is reverse and the later phase is dextral. So overall in the area, we have like variable amount of complexities, and also the kinematics are not uniform. So using our structural information and basement rock distribution, we come up with a new solid geology map of the Mount Roots area. And we use this solid geology map in different time slices to show the progressive evolution of the area. So our first time slice is the early Paleoproterozoic time slice, and it shows that the tectonic relationship between the Christie and Mount Roots domain, it shows that during this time we have a major extensional event happened during the early Paleoproterozoic, because the east-west trending southern overthrust or Curry shear zone accommodated the early Paleoproterozoic sediments against the Archean Christie domain. We inferred that the Cairn shear zone and also possibly the Skylark Spire Hill shear zone, they also developed as an early extensional structures during that time. During the late Paleoproterozoic Kimman event, deformation, metamorphism, and magmatic processes stopped the sedimentation in the Mount Roots. The Kimman structures are poorly understood and mainly recorded within the central part of the Mount Roots. The kinematic indicators within these structures are very poorly understood, and we don't have enough evidence. Therefore, the stress orientation during the Kimman is more speculative and based on the previous literature from the southern Golar Craton. The end of the Kimman event is marked by the intrusion of the engineered adamellite, which is like 1690, and also the development of Condamina metaconglomerates, which exist, we found only in this point. The Tanzania time slice is a more magmatic and volcanic event. We have the Balta granite all over the Mount Roots, and also the Golar volcanics, which occurs only in the southern part of the Mount Roots area. This Tandoor time slice is like immediately followed by or slightly overlapped by the Paleo-Mesoproterozoic Carrara events. So during this Carrara event, most of the structures become reactivated, or we have new structures developed during this time. Especially, we can see that in the central part we have refolded the older structures. In the south, we see this southern overthrust become like a reverse reactivation. And we can see this, whatever this Bulgarian shear zone is running northeast, and also the Carrara shear zone, they become like a sinistral fault. We can see the opposite kinematics along this Skylark Spire Hill and Jupiter shear zones. And also we can see again the reverse reactivation along the Carrara shear zones and the Cairn Hill shear zone. This indicates that possibly during this time we have a north-south shortening. This Carran event was followed by the Mesoproterozoic Corabi event. During this time, we have another phase of structural reactivation happens. We see most of these northeast trending structures now become like a reverse fault, like the Bulgania as well as the Carrara shear zones. And whatever we have these east-west structures in the north especially, they become a more dextral structures. Even this, the east-west section of the Carrara shear zone and as well as the Cairn shear zones and also further north. We have also some folding during this time. So all of these structures indicate that possibly we have shortening along the northwest-southeast trending during this time. This Corabi event was followed by an extensional event, which is resulted the deposition of the Carioli basin in the southeast, and also during this time, some part of the Vulcania shear zone becomes like a normal fault. So, in summary, new solid geology map of Mount Woods through certain project can help in unraveling basement complexities using different time slices. Structural geometry, kinematics, and timing of activation or reactivation of the major shear zones can be linked to stress orientation of the different tectonic events. Potential of the pre-existing structures and possibly the basement architectures played a key role in the reactivation history of the major shear zones. And finally, the time slice systems helps to understand the changing kinematics during reactivation, highlighting the controls of fluid flow and consequently the mineral potential. Thank you.